welcome to the lecture video for section 5.3, which is all about the definite integral. So if you remember in section 5.2, we saw how to write the approximation of area under the curve with n rectangles using sigma notation, so using that capital sigma symbol, the sum symbol. And we saw these things called Riemann sums, and so these were the approximations of area under the curve using rectangles. We then saw how to compute the exact area under the curve by taking the limit as n goes to infinity of the nth Riemann sum, which we've called Sn. So notationally, what that means is that we have that our area under the curve is the limit as n goes to infinity of the sum of, from k equals 1 to n, of f of ck times delta k. And if you remember that f of ck there, that is your height of the rectangle. So ck is whatever endpoint you've chosen to use to determine the height. F of ck is then your evaluation, so the y value of your function at that endpoint. And then delta k there, that's the base length of each of your rectangles. And so delta k in our method that we've seen is always just the same thing. It's the length of the interval divided by n, however many rectangles that you have. And so if we were able to take the limit as n goes to infinity of this, then that would give us the exact area. So if there were infinitely many rectangles underneath the curve, we would no longer be approximating that area. The area would be exact. But we don't exactly know how to take the limit of that. And that, again, I said this is something that's been cut from the course, but you can find taking the limit of these Riemann sums in the textbook if you are interested. But today we're going to look at some new notation for the area under the curve. And so if you remember in section 5.2, I sort of alluded to the fact that the area under the curve is related to the antiderivative. And this new notation might make you believe that even more. So we're going to begin with a definition here. So let's let f be a continuous function on the interval a to b. Then we represent the area under the curve, which is the signed area. So remember, if the function has negative y values, you might end up with some negative area. So we represent the signed area under the curve on this interval with something called the definite integral from a to b of f of x with respect to x. So that is, the way that we write this is that the area a is equal to, so it's the integral from a to b, so you put the smaller number on the bottom, so from a to b of f of x dx. And so this notation should look really familiar to you. Before we had the indefinite integral, and the only difference in the notation is that there weren't those numbers a and b attached to the integral symbol. And so when you do not have the numbers a to b attached to the integral symbol, that's called an indefinite integral. And the answer of an indefinite integral, the way you compute it, is you find the antiderivative. For a definite integral, what we're saying, the result of the definite integral is the area under the curve. And because the notation is so similar, at this point, what I want you to be thinking is that hopefully at least these two concepts are related to each other. Why else would we want to use the same notation for two things if they meant totally different things? And so when we get to the fundamental theorem of calculus, which is section 5.4, we're going to see this relationship between the definite integral and the indefinite integral. But for today, we're going to focus on this definite integral here. So specifically, we're focusing on the area under a curve. So the note that I made here pretty much just captures what I said. So the notation used for definite integrals is similar to the notation that's used for indefinite integrals. The difference is that the definite integral includes bounds a and b. So let's just recall what I just sort of said. So if we say that capital F of x is equal to the indefinite integral of little f of x dx, well, what we're really saying is that capital F of x is our antiderivative. So that means, if it's the antiderivative, that means that when we take big F of x prime, we get little f of x back. Okay, so the question that we sort of hope the answer is yes is the following. is there a relationship between area under a function So is there a relationship between the area under a function and the antiderivative of that function? It's very slow to write with a stylus. So, and the antiderivative of that function. Because we use the same notation, so we should hope that there is a relationship. And if we remember back to that velocity example where I drew the velocity curve, we found the area under the velocity gave us the distance. And we know that the distance function is also the antiderivative of velocity. So we can see that there was a relationship between the antiderivative and the area under the function. Okay. So let's look at an example here. Let's consider the graph of this function that's given here. And so this function is kind of strange looking. Clearly it's a piecewise function, but it is continuous. And notice that when we're talking about the definite integral, we didn't say anything about it being differentiable, right? We talked about it being continuous on the interval, and it is continuous on this interval. So the first question, the first example, is asking us, what is the definite integral from -7 to -1 of f of x dx? Well, we're asking for the area under the curve between x equals -7 and x equals -1. So if I were to shade that in, what it would look like is it would be this area here and this area here. And so what we see is that our area is actually two nice shapes, right? It's a triangle and a semicircle. So we can break this. Into two shapes. Because we have nice formulas for the area of a triangle and the area of a semicircle. If it wasn't a nice shape, we would have to use an approximation like the Riemann sum, right? We'd have to use rectangles to try and approximate what this area is. But because it's nice shapes, we can actually compute this directly. So what I'm saying is that the definite integral is going to be equal to the area of the triangle plus the area of the semicircle. Okay, well, we know the formula for the area of a triangle. It's 1/2 base times height. And the area of half of a circle is going to be half of the area of a circle, right? So half of pi r squared. And so let's plug in the numbers that we have for that. So looking, I'm just going to scroll up a bit here. So let's look at our triangle. The base length is from -7 to -5. So the base length is 2. And the height is also 2. So it's going to be 1/2 times 2 times 2. And then for our semicircle, we scroll up, we just need to find the radius. Well, the radius, you can look between -5 and -3, or -3 and -1, but we see that the radius is 2. So our formula for the area of the semicircle is going to be 1/2 pi times 2 squared. And so if we simplify this, we can cancel a couple 2's, and so we end up with 2 plus 2 pi. What it works out to. So that's our exact area under the curve between x equals -1 and x equals -7, but it's also the value of our definite integral. So the definite integral is the signed area under the curve. They are the same thing. So for the next example, we want to find the integral from -3 to 5 of f of x dx. So if we scroll up from -3 to 5, we've actually got quite a few shapes. So I'm just going to change the color of my pen here for a second. So I'm going to color this in red. So between -3 and 5, we're going to be looking at this area here. So we've got this quarter circle from -3 to -1. We've got a triangle between -1 and +1. We've got another triangle between 1 and 2. And then between 2 and 5, we have this square, or yeah, I think it's a square. Okay, so we'd like to, I'm just going to switch back to black. Okay, so we'd like to compute the area of all of these shapes. And so when we do that, we get that it's equal to the area of this quarter circle, that's my best picture, plus the area of a triangle. Now notice, I'll scroll back up, the second triangle that we have between 1 and 2, x equals 1 and x equals 2, is below the x-axis. So these have negative y values, which means that this area is going to be considered negative when we're talking about the signed area, which the indefinite integral represents the signed area. So we actually want to treat the area of this triangle here as a negative value. So rather than writing plus the area of the triangle, I'm going to write it as minus the area of the triangle and minus the area of the square, because we know that those actually have negative area when we're talking about signed area because they fall below the x-axis. So minus the area of the triangle minus the area of the square. So now it's all just a matter of knowing our geometric formulas. So the quarter circle, that's going to be 1/4 pi r squared. For a triangle, it's 1/2 base times height. For the other triangle, it's also going to be 1/2 different base and different height. So maybe I'll call it B1H1 just to sort of represent it's a different base and a different height. And then minus my square, which I guess I could say is length times width. Okay, so plugging in those values, we can see that our radius is still going to be 2 for that circle. It's actually the same circle we were talking about in the above example. For our triangle between plus and minus 1, our base length is 2 and our height is 3. For the triangle that falls below the x-axis between 1 and 2, the base length is 1 and the height is 3. Now notice I don't have to put a height of -3 because I've already put the negative sign out in front to denote the fact that this area is negative. And then for the square, the length and the width are both the same. That's why it's a square, and it's 3 times 3. So when we work this out and simplify it, we get 2 pi minus 15 over 2. And so that's going to be the area, the area underneath the curve, the signed area, and that's also the same as the definite integral value. So as long as your curve has nice shapes, you're able to compute the value of the definite integral because you're able to find the area of these nice shapes. If you don't know, or if you don't have a formula, a nice geometric formula for the area, then we need a better method in order to do this. And so that's what we'll be exploring in section 5.4. So there's quite a few properties that are associated with a definite integral. So we'll talk about them each one at a time. So the first property, so property 1, we say the integral from a to b of f of x dx is equal to minus the integral from b to a of f of x dx. So if you switch the order of your bounds on your integral, what we're saying is we want you to switch the sign of your area. So if your area was positive, you'd now make it negative, and vice versa. You can imagine it as, when we're talking about the signed area, we're talking about going from the left to the right with our bounds on the interval. So, you would go from 1 to 4, not from 4 to 1. And what it's saying is if you go from 4 to 1, which can happen, so sometimes you will see an integral, maybe I'll just give you an example. You could see something like the integral from, I don't know, 3 to 1. So you can then sometimes see the bigger number on the bottom. And if you do, and you're uncomfortable with that, what you can do instead is switch it to be negative the integral from 1 to 3. So you can switch the bounds, but whenever you switch the bounds, you have to change the sign of your integral. So it changes the sign on your area. Okay? The next point, point 2, property 2, is saying the integral from a to a of f of x dx is equal to 0. So this should actually be intuitive. I'm actually going to write this down. So this should be intuitive. And the reason it should be intuitive is because we're talking about the definite integral represents the area underneath the function between those two bounds. Well, the area between a and a is, we're talking about the area under a point. And the area under a single point, there is no area of that, right? It would just be a line. So this should be intuitive, since the area under a single point is going to be 0. There would be no shaded region because it's just a single value. So the area under a single point is 0. My writing is very messy today. I'm trying to make it a little better. Okay, third property. So this one is very similar to, same as derivatives. When there's a constant involved there, you can just pull it out in front. So if you want to find the area between a and b of some function k times f of x, that's the same as finding the area between a and b of the function f of x and then multiplying it by k. So if you think about it, what happens when you multiply a constant in front of a function? That's a vertical translation by a factor of k, right? So it's going to be either going to be stretched or compressed, depending on whether or not k is a fraction. And so, sorry, I should say it's a vertical expansion or a vertical compression. It could be either of those things. And so all that's going to happen is it's going to increase or decrease your area by the same factor. And so that's why we can apply the k before, or we can apply it after. The fourth property is similar again to derivatives, and it's saying that we can add and subtract the areas. So if we want to find the area of two functions added together between a and b, we can do it separately. So we can find the area of the function f of x and then add it to the area of the function g of x, and we can do it that way, or subtract it depending on what you'd like to do. So that's property 4 there. Property 5 is saying that we can split an integral up. So if you wanted to measure the area between of a function between a and c, so maybe I'll just sort of like draw a picture for us here. So imagine we had some function, this is f of x, okay, and let's say that this here is a and this here is c, and I wanted to find the area between a and c. Okay, so my goal is to find the area between a and c. And let's say b is some value between a and c. Well, what we're saying we can do with the integral is we can find the area, entirely between a and c, or we could find the area between a and b first. And then we could add to it the area from b to c. And that's going to still result in the same thing as the area from A to C, because, if I do it here, let's say in blue, the area from A to C, of course, is just this whole region. And so if you add up the black lines and the red lines, those areas, you end up with the same lines that the blue lines are covering. So this is what property 5 is saying, is that you can split up a definite integral with any numbers in between the two outside bounds. So let's work through an example, and we're actually going to do a couple of these examples. So the first one, we have some information. So we know that the area underneath the function f of x between -1 and 6 is 8. We know that the area under f of x between -4 and 6 is -3. And we want to determine the area between of the function, underneath the function between x equals -4 and x equals -1. And so rather than trying to draw some sort of a function that has this property, I don't actually try to do that. Instead, the way that I do this is I draw a number line. And on the number line, I want to put the biggest number that I've seen on the far right. So the largest bound that I see is 6. Okay. And then I want to put the smallest bound that I see on the far left. So the options for the smallest bound are -1 and -4, but -4 is the smaller number. It's more negative. So then the only other number that I see is -1, so I'm going to put that where it belongs on the number line. And so from there, I'm going to summarize the information that I have. So I know that between -1 and 6, so this region here, I know that my area is 8. So I'm going to put an 8 there. Okay. Between -4 and 6, so this large region here, I have an area of -3. So then between -4 and 1, which is the value that I want to try and determine, how do I figure this out? Well, I know that this value here, let's call it x. So I know that x plus 8 needs to equal a total area of -3. And then it's just a matter of solving for x. So x is going to equal -11. So if that value of x there, if that's an area of -11, and then I add it to the area of 8, the overall area would be -3, which is what we want. So to conclude my answer then, I would just say that the integral from -4 to -1 of f of x dx is equal to -11. So I'm using this idea that I can break up the integral. So that comes from property 5 that we just saw above. So the idea that you can break up an integral from -4 to 6 into two pieces, the integral from -4 to -1 and the integral from -1 to 6. Okay, and I find that this is the best way to do it, is using a number line. Okay, so our final example is a practice question. So, if you want to pause the video and take a few minutes to try this. This one is a little bit tricky because we have two functions. We have f of x and we also have g of x. But g of x, we actually know the exact value we need to know. F of x, we've got a whole bunch of information about. So, okay. If you want to pause me, I guess now's your chance to do it. So, okay, when I'm looking at this integral here, the first thing that I notice is that this integral here, I'm going to circle it, is an integral from 8 to 8. And so using property 2 above, I know that that integral is equal to 0, right? Because the area under whatever function, it doesn't matter how complicated that function is, the area under that function at x equals 8 is exactly 0. So we don't even need to worry about computing that. So really, all we need to do is we want to compute the integral from 3 to 5 of this function here. So 2 times f of x minus 5 times g of x dx. And so we're going to use a couple of the properties that we saw above. So the properties above told us that we can break up this integral, right? The fact that we have two functions subtracted means that we can break it up into two integrals and subtract the integrals. So that would mean that we have the integral from 3 to 5 of 2 times f of x. So we find the area of that function, and then we would subtract it from the area of the function 5 times g of x. Okay. But we've got another property, I think it was property 3, that told us when there's a constant that's multiplied by a function, we can actually just pull that constant out. So we would have 2 times the integral from 3 to 5 of f of x dx minus 5 times the integral from 3 to 5 of g of x dx. Well, okay, let's look above at the information that we have. We actually know the integral from 3 to 5 of g of x dx is equal to -1. That's one of the properties that we've been given. So we already know that this piece is equal to -1. Okay, so really we just need to figure out what this piece is here. We want to figure out what the area underneath f of x is between 3 and 5. And for that, again, looking above, we have 3 pieces of information here. We know the area between 1 and 7, 1 and 3, and 7 and 5. Now, when I look at this third area that I've been given about f of x, the integral from 7 to 5, I don't like that the bigger number is on the bottom. I don't like that 7 is on the bottom. And so using property 1, I can flip the bounds. So I can put the 5 on the bottom and the 7 on the top. But then that means that my area is going to be the opposite sign. So before, the area was -9, which means now it should actually be +9. because I flipped the bounds. Okay, so we're going to use the same strategy with a number line on the bottom to figure out what our desired area is. And so I want to look for the smallest number I have on the bounds, which looks to be 1. And the biggest number I have on the bounds looks to be 7. So I'm going to start off by drawing a number line. So this is for f of x. And my number line is going to go from 1 to 7. Okay, so the other values that I have on the bounds are 3 and a 5. So I'm going to place those on there. Okay, so scrolling above, let's do it one at a time. So first I have the integral from 1 to 7 of f of x dx is equal to 10. So I want to acknowledge that from 1 to 7, so 1 to 7, this whole region is equal to 10. Okay, the next one that I have is from 1 to 3, and it's equal to negative 6. So between 1 and 3, this area is negative area, and it's minus 6. Last but not least, I have the area between 5 and 7, and I know that that is positive 9, right? If I did 7 to 5, it's negative 9, but we want the interval to go from the smallest number to the biggest number. So it's an area of positive 9 between 5 and 7. So this is positive 9. So we want to figure out what this area is here, between 3 and 5. That's exactly what we're trying to figure out. Well, we know that these three numbers, negative 6, x, and 9, have to add up to the number 10. So we know that it's negative 6 plus x plus 9 needs to equal 10. And so this allows us to solve for x, and we see that x has to be 7. So that means putting this all together, my definite integral ends up being 2 times 7 minus 5 times negative 1, and I end up getting that it's 19. So then that means that my answer is going to be D. Okay, so that's it for section 5.3. Next week we're going to do the last two sections of the course, and so that's going to be sections 5.4 and 5.5. We'll be talking about the relationship between the definite integral and the indefinite integral in section 5.4. And then in section 5.5, we're going to see some ways to find antiderivatives of some complicated functions. So thank you very much for listening, and I will be making more videos soon.